Now that we have this idea of friction factor and head loss, we have to relate this to the other important parameters in the flow: pressure, elevation, velocity, and so on. And we do that with the extended Bernoulli equation. So if you remember from the energy equation, when we assumed uniform flow, we ended up with this. We already talked about how the variation in internal energy is the head loss. So the conversion of mechanical energy into thermal energy by friction. We also need to walk back our assumption that the velocity is uniform. In viscous flows, the velocity is not uniform anymore. So we introduce this integral for the velocity difference that comes from the control volume definition of the energy equation. And we simplify this by introducing the kinetic energy coefficient, or alpha. Alpha is what we call a covariance. It's basically the ratio between the square of the average and the average of the square. For fully developed flow, in laminar flow, you can actually do the math with the parabolic velocity profile, and the value of alpha is 2. For a completely uniform flow, alpha would be 1, and we would be able to recover the initial form of the velocity term in the Bernoulli equation. Now, for turbulent flow with a 1/7 power profile, we can actually find that the value of alpha is 1.06. If we look at the universal velocity profile, the value of the kinetic energy coefficient ranges from 1.03 to 1.08. In general, alpha equals 1 is a reasonable approximation for most turbulent flows. Part of the reason for that is because this difference is usually very small compared to the pressure and elevation terms and the head loss. So most of the time we're just going to assume that alpha equals 1. However, for certain applications, for instance certain types of nozzles and things of that nature, where there's a large velocity difference or where higher accuracy is required, we need to be more careful and use a more accurate value for the kinetic energy coefficient. So then we can actually complete our definition of the extended Bernoulli equation, which includes the head loss and the additional kinetic energy coefficient. Now, it's important to note here that there are two forms. The top equation here is in terms of energy per unit mass. The second form of this equation on the bottom we divide through by gravity, and each term in this equation has dimensions of length. This equation is often used in industry because length is more relatable. It's easier for us to envision. But the first equation is the one we get from the energy equation, and the one we're going to use for the most part in this class. Now that we have the head loss, we have the total head loss, we need to take a little bit of a closer look at what goes into the total head loss, and it's actually the sum of two parts. We've already looked at major losses, which are due to friction in fully developed flow. So we use Poiseuille's equation or the Darcy-Weisbach equation, and then we have something like the Kolberg equation for a friction factor. However, in many cases, the fluid also must pass through fittings and valves and things like that. When this occurs, the fully developed velocity profile becomes disturbed, and you can have boundary layer separation and additional flow development. And this creates additional pressure losses or head losses, which we call minor losses. Some minor losses are expressed using the loss coefficient, K. Sometimes they're expressed using the equivalent length, or L sub E. So you can see both of those formulations here on the slide. In this case, if we're using the equivalent length, you still need to have the friction factor for fully developed flow. It's also important to note that minor losses can be much larger than major losses if you have a lot of fittings or certain types of fittings. The difference is just terminology. Major losses are always present for any flow. Minor losses may be present if these kinds of fittings are in the system. We can find the values for minor loss coefficients or equivalent lengths in tables and graphs like the ones that are shown on this slide. More complete sets are included in almost all textbooks. It's also important to note that K can vary with pipe size and flow conditions. It's frequently used in industry because it's easy to calculate, but it can be specific to a type of products. The values, like the ones in the tables, are representative. They're kind of average or typical values, so they may not be very accurate. The equivalent length tends to be constant with pipe size. It's a little bit more reliable parameter. However, you always want to go to a product document and look up the method that they use to characterize the losses through their product. It's always good to look at the product documentation anytime you're looking at a specific item. Just as a quick example, we'll look at this graph. In this case, we're going to assume that we know the flow rate and we're trying to find the total head loss. So we're starting with the major head loss. We're going to get the Reynolds number from the flow rate and the diameter and so on. And from there, we're going to move to find the roughness of the steel pipe that makes up the system. Once we have Reynolds number and roughness, then we can go to the Colebrook equation or the Moody diagram, and we can get the friction factor. We're also going to assume that L over D is given by the problem. We know that from the geometry of the system we're trying to predict. So once we have the friction factor and L over D and the flow rate, then we can find the major head loss. Then we need to look at minor losses. So from the graph on the previous slide, we know that for a square entrance, there's a minor loss coefficient of 0.5. We also can see that there are 4 90-degree elbows here. So again, if we look at the previous slide, we look at the chart for a standard 90-degree elbow, and the equivalent length is 30. And then for exits, we have a minor loss coefficient that is equal to the kinetic energy coefficient. So if we assume that this flow is turbulent, then K would be equal to alpha, which would be equal to 1. If the flow was laminar, then K would be equal to alpha, would be equal to 2. So we look up all these values, and then we can come up with the summation, all the sum of K and sum of equivalent length.